Right, time for some more conversation about Chapter 6. We need to work on the next section, which would be involving talking about dilutions. This would be item number 12 in general from our learning objectives for this chapter. Notice that I have made a correction to the objectives in the last item. We won't be doing that one at the end of that description. So where does it go from here? When we're talking about dilutions, these are things that we do in our everyday kitchen experiences, including mixing up your frozen juice from concentrate, where you take a certain amount of substance and you add water to it to make it more dilute. And so some concentrated thing plus a solvent gives you that resulting mixture. So the point that you have to think about here is that the number of moles of the solute, the amount of solute, remains the same, and all that's changing is the volume of the solution by adding more solvent. And we'll think in terms of molarity and volume of the two solutions. The initial solution is noted with subscript I, and the final solution, the diluted one, will be subscript F. So molarities and volumes of each of these. When we're making this, it's helpful sometimes to use pictorial representations, although I know they're not always people's favorite thing. When you're preparing a less concentrated solution from the more concentrated solution, in other words, you've got the same number of little spheres from left to right, but they're now in a larger volume. So that's what it looks like when it's more diluted in a pictorial representation. If we go back to our definition of molarity, molarity means moles per liter. And so if you rearrange that equation, moles is equal to molarity times liter. And we will use this in the sense of thinking about the fact that the number of moles here in the initial situation is going to be equal to the number of moles in the diluted one. We'll call that the final situation or final solution. And so let's think about that. So the moles of solute before the dilution and equals the moles of solute after dilution. And so if molarity times volume equals moles, then that's what we're going to use. Molarity of the initial solution times its volume equals molarity of the final solution times its volume. We will rearrange this as needed to solve for one of the parts that we do not know. Make sure when you do these things that the initial molarity should always be larger than the final molarity, and the final volume should always be larger than the initial volume. That makes sense. All right. Next slide. So thinking about this with a nice diagram, the volume, in a practical sense, the volume of a solution that is going to be diluted is placed in an empty flask. This one's labeled as a 100 milliliter flask. You figure out how much you need. You add solvent to a level that's just below a calibration mark on the neck of the flask that's shown in the last panel here. And you shake it around, but you start out with just not quite as much liquid to begin with, because sometimes there's a volume change that you do not anticipate as things mix. And then when it seems mixed, you add solvent to reach the calibration mark, and then your flask is good to go. Notice this one will say it's to contain some amount at 20 degrees Celsius. It'll give you how many sig figs past 100 is measured in that particular volumetric flask. Okay, let's set one up. Sulfuric acid, nasty stuff. You should know its formula sooner or later. We'll talk about it in another chapter again. But it's H2SO4 purchased normally at a concentration of 18.0 molarity. M means molarity, moles per liter. And always think in those terms when we're doing these calculations. That means moles per liter. How are we going to prepare a 250 milliliter volume of something much less concentrated, 0.5 molar aqueous H2SO4? So here's where we have to think about what's the initial and the final for the volumes and the molarities and label them correctly to set it up successfully. So the initial molarity is the 18 molar. We call it molar, or you can say molarity. The final molarity is going to be half molar, 0.5. The part that's hardest about this is making sure you get the right thing. The final volume is 250 milliliters. So realize these two go together, because sometimes if we put them together in the equation wrong, it doesn't make any sense. And so what we're looking for is the final volume. the volume of the initial solution, I didn't say that correctly, that would be diluted to make this new solution. All right, so where do we begin? Think about the equation. And it's very easy if you think about it this way. MIVI equals MFVF. And what we're looking for is VI. So VI should be initial volume that we're going to use to dilute will be final molarity times the final volume divided by the initial molarity. So final volume is what we're looking for. Initial volume. I can't say the right thing. Sorry. Is what we're looking for. And so it's going to be MFMI divided by MI times VF from just a rearrangement of the dilution equation. And so put in some numbers. So the final molarity, if we've labeled our things, write them down and label them. It really helps. Otherwise, we get totally mixed up and we don't even know it. So divide that by the initial molarity, 18 molar. Notice that some units are going to cancel if we do this correctly. And we're going to multiply now times the final volume that we're making. That new diluted solution is 250 milliliters. Notice that we do not care about the units here. And so that is going to be punched into your calculator. You get an answer in milliliters because we began with milliliters. As long as the molarity cancels, your units that you plug in are milliliters, your answer is going to be in milliliters, and that's fine. Doesn't give us any difficulties here. So that's how we do this. We're going to take that 6.94 milliliters, if you can measure that very, very carefully, of the initial concentrated sulfuric acid, nasty stuff, to enough water to make 250 milliliters in a concentration of 0.5 molarity. Just as a point of information, and this is just because you're taking chemistry class, so we should be talking about these things in detail. For safety, acid solutions are always added to water. You add acid to water. Acid goes into water. I always learned it as A into W to be sure that you're not going to end up with something that's so hot that it becomes dangerous to handle. Okay, let's do another one that's similar but not the same information, not the same example. And we're going to prepare 60 milliliters of 0.2 molar HNO3, that's called nitric acid, from a stock solution of, I'll write the name for you, of 4 molar nitric acid. All right, so same thing we need to do as always. We need to label the parts that we have and figure out what's needed. The stock solution is going to be the initial molarity. The final molarity is going to be M sub F, this one, the 0.2, and the amount of the final volume of that solution will be the 60 milliliters, so VF. Be sure that you label things correctly or you won't know what you're doing. The dilution equation looks the same as it did, and so now I will mark or write in the pieces we know. The initial molarity is 4, the final molarity is 0.2. The final volume is going to be 0.6 liters, which is the same thing as 60 milliliters. If you don't do it in your head, then you need to take the steps and write it out, but we'll talk about that in a minute too. And then what we're looking for then is the volume of that initial solution that is going to be required to get this properly diluted. The equation rearranges the same as we did on the last one. And so the molarity times the volume of the final solution divided by the molarity of the initial solution gets what we want. Plug in some numbers. Remembering you got to label them correctly or you won't know what you're doing. But molarity times volume in liters gives you moles, which is why we commonly use liters here. And then the molarity cancels, and our, oops, sorry about that. Our molarity cancels, and then the answer we have should be in liters, but it might not be what we want to know because don't really always use liters. It's going to be 0.003 liters. Well, that's not very much. It's 3 milliliters. Remember that 1,000 milliliters is 1 liter, and you can use that as a conversion factor to get from 0.003 liters to 3 milliliters. Now, I was commenting about milliliters. Trying to advance my thing here. So you add 3 milliliters of acid to enough water, which in other words is essentially 57 milliliters, and that should give you 60 milliliters of solution. Could we have done the same, and would it have worked out the same if we had just used milliliters? This is a good question to think about. in a true sense, we're looking at moles of the initial portion equals the moles of the second portion, because molarity is moles per liter times liters going to be equal to moles, right? That's where this comes from. And so you should technically be using liters if what you're looking for is moles. However, when we set these up, as long as what you pay attention to your units, our answer was in liters this time because we put liters in. But if you had put in milliliters instead, you would have skipped the conversion step and you would have ended up with milliliters as an answer. So yes, you can. Just be careful that you're watching what cancels, and that if you put milliliters in instead of 0.06 liters, you put in 60 milliliters, you could, then you would end up with milliliters for an answer. Seems simpler, to be honest, actually. Not a big deal. Again, this is a dilution of an acid solution, and so you should always add acid to water. Whenever handling acids, especially concentrated ones and strong ones, you should do this in a careful manner. All right, how about one more example? This is kind of a different one. Let's say you have a bottle of concentrated hydrochloric acid, and we haven't talked about the names, but maybe you've heard of it. Hydrochloric acid is another one of those strong acids that comes in very concentrated stock solutions, and you tend to dilute it to use it for other things. It's only got a little bit left. You measured out and you found out how much it was, 37.5 milliliters. And so what would be the concentration of this acid if it's diluted to 350 milliliters? All right, so let's think about what we have, what equation we have to use, and what do you know and what do you not know, and what are we going to solve for? So this is always the same thing when you're looking at dilutions. So I would call this the dilution equation. Initial molarity times the initial volume is going to be the final volume equal to the final volume times the final molarity. I said it backwards, same thing. And so what do we know of these variables in that equation, and which one are we going to look for? So the initial concentration, M sub I, is going to be 12 molar. The volume that we have of that initial solution is known. So that's the initial volume. It's 37.5 milliliters. And this time I'm not going to change it to liters, and I'll show you that will be okay. The final molarity that we're looking for, well, that's what we're looking for. We're looking for that right here. What concentration will that be? That's a molarity. And so that's the one we'll solve for. And what we're doing to figure out is if we dilute it to 350 milliliters, that's our final volume. So final volume is 350. So we're going to solve for the final molarity. Not a very difficult rearrangement. This is not tricky math. Pretty simple algebra to be, I hope. Hope it looks easy to you. So the final molarity is going to be initial molarity times the initial volume divided by what's left, final volume. Put in some numbers. Write out all your steps. There is no substitute for being careful on these, because there's 150 ways to make errors when you don't really write things down. And so it's 12.0 molarity times 37.5. Whoops, 37, I can't write. We'll try again. Get the right number here. 37, that's supposed to be multiplied together. It doesn't look like that. 0.5 milliliters. And then we're going to divide it by the final volume, 350 milliliters. Okay, pay attention to your units. What do you see? The milliliters cancel. So the fact that we've done this in milliliters is of no issue. And the answer you get is going to be in molarity, which is the goal of these types of calculations. That's normally the chemist's favorite unit. And so if you get out your trusty calculator, pull yours out, pause the recording, take a look and see if you get the same thing I do. Hopefully you do. And by the time you punch it in the numbers, I got 1.286. Now, how many sig figs honestly belong in this answer? We should always put down several and then think about it, because we often get lazy and don't even think about it. In this question, we have 3 sig figs. 3 sig figs. This is honestly 2 sig figs. So we're going to be left with a smaller number of sig figs than we would prefer. But that's the way it goes. If you don't get more sig figs in your initial answer values, then you have to limit your answer to 2 sig figs here. 2 sig figs will be 1.3 molarity. All right, there's a couple of easy examples or simple examples for dilution. The equation always looks kind of the same, so try not to get it mixed up and be careful to write things out. Good luck on your homework. Ask questions as needed, and I will continue on the next topics on the next recording. See you in class.